class. The week before Thanksgiving.
Yeah.
So let's see, that means next week we have no class, right?
Yep.
Yeah.
That means what?
Because Tuesday is
Friday.
Friday instruction?
Yeah.
Yeah, okay. Yeah, so we should do something special, like give you extra homework or something. Okay. All right, so any questions before we get going?
Like it's on the sample. You explained it to me after class, but I kind of forgot. But the sample in between the application that we did the last time, like the device called a sample that does the absorbing. Is that all it does? It just absorbs the.
Yeah, so you have a material, and for whatever reason you care about its absorption spectrum, and so you need to be able to determine what that absorption spectrum is.
Okay.
So that's what our discussion was about, is how you measure that.
Okay.
And if you're in the visible and near IR, no big deal, use a spectrophotometer or spectrometer. If you're in the IR, then that's a problem, so use an FTIR.
Okay. Yeah.
Yeah.
I had a question from 6 part B, I think it is. And I don't have the
It's
actual
problem
problem
6?
in front of me. Yeah, if you pull that out for me. Thank you.
Oh, yeah, okay.
Yeah. So as we were wrestling with it, for the interference term on the irradiance, as we're trying to come up with, okay, how do we want to go about doing it? One of the ideas that I kind of came up with was, okay, does the amount that the interference term impact everything else depend on like the cosines of how in line they are with each other, or?
So we have beams instant like this, electric field out of the board,
Yes.
right?
Yes.
And so this is theta, that's theta.
Mm-hmm.
Okay, so then these two are parallel, so the dot product is going to give us 1 of the polarization state vectors.
Mm-hmm.
And then if we plot the irradiance here, we're going to get something that looks like this, a linear fringe pattern.
Mm-hmm.
And this separation depends upon that angle.
Okay. So, okay, that's a different way of thinking about it. Because what we were, working with Zach and Wes, what we were wondering is, would the actual like interference term on the irradiance like equation itself, would the degree that it interferes with each other depend on like what angle they're at with each other, or?
No.
No.
They're polarized in the same direction.
Okay.
So
Yeah.
the dot product will give you 1. And then when you look at the interference term added to the 2 DC terms, it just gives you a sinusoidal interference pattern.
Makes sense.
So that's the classic way to make a linear interference pattern.
Okay, which makes sense. And I may have to ask you a little bit more about this after class. So.
I guess just as a carry-on point to this, we don't really care what angle they're coming at in relation to each other at all. So it's the
Well, I
same.
mean, that's going to determine what the period of the interference fringes is.
Mhm.
So in that sense, yeah, we care about that. But
But then, like a beam, 2 beams propagating on top of each other in the same direction, as opposed to a beam propagating one way and a beam propagating counter, those would be the same. They're both parallel to each other, right?
Well, so we're trying to find the irradiance in this plane, the XY plane.
Right.
And so in that case, the surface normal is z hat. And so we've gotten the complex pointing vector. And so we need to dot it into z hat and take the real part, take the absolute value, And then that will tell us what the irradiance is in that plane. And if you follow the map, it'll just all work itself out. And then what you end up getting is this linear fringe pattern. Okay, question?
I can ask you this afterwards if it takes too long, but it's more of a clarification
Okay.
type question. So with number 4 and 5, David and I pretty much thought that you would just use the delta phi term or the phase difference term in the interference term, I guess, in the irradiance equation to solve for the wavelength and the refractive index.
Yeah, that's what it boils down to. So in number 5, for example, you have this Michelson interferometer, and then in one path you've got a 5 centimeter long gas chamber. And so it starts off with, I think the refractive index here to begin with is vacuum.
Yeah.
Vacuum.
So that's 1. And then at the end it's air, and that's whatever it is, what we're looking for.
Okay.
So if we look at the optical path difference, then it's going to be, for whatever the condition is, it's going to be 2 times whatever the, actually, let's say that's D,
Okay.
and then whatever the refractive index difference is,
Yeah.
which in this case is going to be ampere minus 1.
Yeah.
And the optical path difference is, 44 fringes, so 44 wavelengths?
Yeah. And the wavelength we assumed was the same as the wavelength that we solved for.
For
in number
cadmium
4.
lamp.
Yeah. Mhm.
Okay.
Yeah, yeah. And so now we're just solve for refractive index of air.
Okay.
Yeah. Okay. Any questions about that or anything else? Zach, are we good?
Good.
Okay. All right. So last time, what did we talk about? Light, yes.
And look at FTIR.
Yeah, so we looked at examples of Michelson interferometer use, and we found that you can set up a Michelson interferometer so that you get Hayden's fringes, and we looked at some applications of that to measure coherence. And today what we want to do is say a few words about setting up a Michelson interferometer to measure or to induce Fizeau fringes. And we've actually already talked about it, but we'll do it in a little bit different context. So, and this leads us to giving the Michelson interferometer a different name. And that's a Twyman Green interferometer. But it's basically just a Michelson interferometer set up like this. Start off with a point source, collimate the light, run it through a beam splitter, and then the upper path, just have it reflect off a mirror. And then the horizontal path, let's say that we have a lens and we want to test how good the lens is, meaning how well it creates a spherical wavefront. So this lens should be creating a spherical wavefront here. And if we were to put a mirror that's a sphere of the right radius, then what should happen is that spherical wavefront will come in and be normally instant locally everywhere on the mirror, and therefore reflect back just in the opposite way that it propagated to it, and then the lens should turn it back into a plane wave, and then it should come back over here, and then we look at the reflected part, and now that's collinear with the reference wave that came from the upper part. And so if we stick a lens here, we can actually image any path differences over here compared to over there. So in other words, we're basically creating a situation where we're looking at Fizeau fringes. We're imaging a region of path difference, but the path difference is separated between two different paths. So this is basically creating some wavefront coming back, and if it was perfect, it would just be planar. But in general, if this has any aberrations or other sorts of problems, it will not be planar, and then we'll have a planar wavefront coming from this reference arm, and then those two superimposed on top of each other we image, and it's the same thing as imaging a region of refractive or optical path difference. And therefore we get Fizeau fringes over here in this image plane, and we can therefore test the optical quality of whatever optical element we want, as long as we have some reference surface to provide a reference for that optical element. Yeah.
That box and everything there, does that include another lens and a mirror at a minimum, or is it just kind of like a sample also there that's?
So it's some optical element we want to test, and then a reference surface for that test. So for example, if we had here instead a prism that we wanted to test, so something like this, then the prism is going to bend the light down this way. In this case, we'd want to have an optically flat mirror to take the light and cause it to go back through the prism in exactly the opposite way that it came through initially. And if the prism's perfect, then we'll end up with the planar wavefront over here coming back out. But if the prism, has some defects on the surfaces, then the wavefront is not going to be planar, it's going to have some variation. And then we compare that wavefront with a planar wavefront from the other arm and image the two, or the interference of the two, and that gives us Fizeau fringes.
So if the fringes are like really crisp and even, then you know that it's good?
Then you know it's bad.
You know it's bad?
Yeah, so in other words, what you want is a region, you want just uniform intensity here,
Okay.
which means that the two beams coming in have the same wavefront.
Okay.
So if you see any fringes, then that means that this wavefront is not the same as that spatially, and therefore there's some problem with it.
Gotcha.
So if you're testing a lens, you could be looking for what kind of aberrations it has. Like, for example, if you have astigmatism, which means that if you've got light coming through this, that it focuses down to one place in one plane, but in an opposite plane, or orthogonal plane, it focuses a little bit behind it. So in this plane, you focus down here, in this plane, you focus down back there. So that's astigmatism. So if you have an eye problem where you have an astigmatic eye, that's what's going on. In one plane, your lens and optical system is doing good, focusing on your retina, but in the other, it's not. It's focusing behind or in front of the retina. And so then you need a lens to correct that. But if you have a lens that has astigmatism in it, then here in the image plane, you'll see something that looks kind of like this sort of fringe pattern. And then you've got astigmatism in your lens. On the other hand, if your lens has coma in it, or let's say spherical aberration, then you'll end up with a series of fringes kind of towards the edges. And then spherical aberration is when you have rays that are close to the axis that focus to one point, and rays that are further away from the axis focus to a different point. And so with a spherical lens, I mean, you always have spherical aberration because these surfaces are spherical, which are not what they need to be, which is namely parabolic. So with when you're trying to get rid of spherical aberration and you can't do anything about the lens, what you do is you just take the aperture and reduce it so you're only using a region right around the central axis of the lens, which also means you're throwing away a lot of light. So you're decreasing your optical efficiency. But in some cases, that trade-off is worth it.
Don't you throw your focus way far out too?
Well, then you're just going to have whatever focus that central region gives you. So, yeah. So at any rate, there are a whole host of different aberrations you can have, and this is one way of testing the lens to see what you've got.
Is it optically? When they
Um,
look into your eye?
So, actually, what they do is they have a whole series of lenses with different focal lengths, different amounts of astigmatism, and what they do is you're looking through the little gizmo at some chart, and then they're just throwing different lenses in front of your eye, one after the other, and you're saying, is it better or is it worse in terms of how sharply you see the letters on the chart. And by figuring out what lens is in front of your eye, you see that thing sharper, then that allows the optometrist to know what your eye problem is. So, and if you've got astigmatism, then they'll put an astigmatic lens in front of your eye, and they'll rotate it. Because the astigmatism isn't necessarily, this plane versus that plane. It could be at an angle like this. And so I've got a little bit of astigmatism in one of my eyes, and it's rotated, I think, 7 degrees. So
And you wear contacts?
I only started wearing these 2 years ago because for my adult life, I've had perfect vision. 2010 in one eye, 2015 in the other. Just fantastic vision. And then when you get older, have I explained how this works?
It gets hard or something.
So in an eyeball, you have the cornea here, and that provides most of the optical power to take light coming in through the pupil, which is back here, and focus it to the retina. But you also have a few other surfaces in here that provide some optical power, and then you have the protein crystalline lens that provides a variable amount of optical power. And then around that lens, you have this annular muscle that squeezes it. And so most of the optical power comes from this surface, a little bit from the other surfaces, and then the finishing touch is that lens. And that lens is what helps you focus light to the retina. And then what happens is, in a completely relaxed state, then the distance away that is focused here to the retina is basically infinity. So anything long distance with your eye fully relaxed, if you have a great eye, then you're focusing to the back or to your retina. And then how far away is infinity? 15 feet. And then you're pretty much fully relaxed. And then as you take something and you bring it in closer and closer and closer, what happens is that annular muscle squeezes that lens more and more, causes it to bulge out, giving you more focal power. And then at some point, you get to the minimum distance you can focus to. And that's called your near point. So this is your near point, and then this is your far point. And so, if you are, say, short-sighted,
You can't see far?
what that means is your far point is not an infinity, it's somewhere, a finite distance away. And so that's your starting point. You cannot focus anything beyond that distance, because that's your far point. The lens is as relaxed as it's going to get. It's giving you the least amount of optical power it can give you. And so you're just done at that point. Then as you start to squeeze that lens, you take the distance that you're focusing and bring it in. And now if you're nearsighted, then your far point is not that far away, which is bad, but your near point is closer, which, can be good. So what you need is basically to put a negative lens out here to take your far point, which is wherever, and push it out to infinity, which simultaneously takes your near point, which is really near, and push it out to kind of a normal distance. If, on the other hand, you're farsighted, what's happening is that in the relaxed state, you're not bringing infinity into focus. In fact, what you have to do is apply some pressure to that lens and get some more optical power in order to bring infinity into focus. And then what that means is you continue squeezing on it, bringing your focal distance in closer. Your near point is kind of further away than normal. So that range that you can focus over, you've got to use up some of it to bring infinity into focus. And that's what being farsighted is all about. And I'm a little bit farsighted. So, so I've got to have a positive lens in front of my eyeball. But for most of my life, it didn't matter. I had enough range here that I could accommodate, far away and close, and it was no problem. But as you age, the problem is that lens becomes harder. It stiffens up, which means that annular muscle, it just can't squeeze it enough anymore to get it to bulge to give you enough optical power to bring near things into focus anymore. So as you age, what happens is your near point, whether you're farsighted or nearsighted, starts marching out. It usually happens around the age of 40. And then as you age, it just keeps going out. And then you need glasses to bring it back in. So generally, you need reading glasses. So I'm 58. When I was about 41, I noticed my near point was starting to move out. And so I would just go down to, Costco or wherever and get some cheapo reading glasses. And that was fine for, 15 years or so. But as my lenses continued to harden, it no longer became fine. So I had to do this. Which is a long way of saying, when it comes to contact lenses, I was an old guy when I needed to have them. And 2 years ago, I tried them out, but it just doesn't work. So, and the problem is, as you age, you also tend to have drier eyes, and dry eyes with contact lenses just doesn't work at all. So, yeah.
How about the laser surgery? Like, do they just cut the outer?
Yeah, laser surgery, all they're doing is they're taking this cornea and they are ablating it to change the shape. Either they're giving you more optical power, or they're coming in and shaving off some in the middle to give you less optical power. So, if you're short or nearsighted, then they're going to give you less optical power. If you're farsighted, then they're going to give you more optical power. So it's basically just coming in with a high-power laser, these very intense pulses, and when that pulse hits your cornea, it blows off, burns off some of your structure there. So, and then you can sculpt the shape with that. So for certain types of eye problems, that's a beautiful solution. Really works well. So, if you're walking down the hallway and you see someone who's wearing glasses, it's trivial to tell whether they're short-sighted or farsighted, I mean nearsighted or farsighted. So, if you're farsighted, you need a positive lens. And so what happens, like Yixon, you're farsighted, what happens is that if you look at the person's eyeball and it's larger than normal, that's because they have a positive lens there. It's a magnifying lens as far as you're concerned as an outside observer. On the other hand, if you look at their eyeball and it's smaller than normal, it's because they have a negative lens in front of their faces and it's acting as a demagnifier. And so you can tell that the person is nearsighted. And if you can't tell just by looking at the eye size, then you look through the side a little bit and see the shape of their face. And does it match up with what's outside their glasses? If it's a little bit in, then you've got demagnification, they're short-sighted. If it's a little bit out, then you've got magnification, so they're farsighted. Yeah, so it's very simple to tell.
What about for like an astigmatism? Can you tell?
Can't tell that. No. Yeah, now, if they would let you borrow their glasses, yeah, you could tell that. Because that is just basically taking a collimated light source, which is as easy as just having a light bulb, 5-10 feet away, and then just using the glasses and taking the glasses and having them be orthogonal to the direction coming from that light source, and then putting up a piece of paper, and then just moving the thing and observing how far away does it take to focus the light. What's the minimum spot? And is it the same, this way and that way? If it's not, well, then there's astigmatism there. So, yeah, so it's easy to tell. Okay, so now you know all about it, and you know what to look forward to as you get older. Yeah.
So are there systems that are not like humans, but like something we built where they use a lens similar to the eye, where you can squeeze it and change how it focuses? Because
Sure.
I feel like
Yeah.
lenses are most often just glass, right?
Yeah. Mm-hmm.
But are there systems where it's like a flexible lens?
Yeah, there are. Mm-hmm. So any of you who've done clean room stuff with PDMS, you could make a lens that way, a variable lens. Turns out I've got a patent on how to do a variable lens with a lip crystal material from, I think we did this in the 90s sometime. Yeah, probably the late 90s. And so, yeah, there are a bunch of different ways of doing it. But generally speaking, you'd want to have your variable lens together with a fixed lens that gives you most of the optical power that you need, and then use the variable lens to kind of tune it. Usually that's how it goes. Yeah, but there's a bunch of ways you could do that. Yeah.
Are these typically engineered on like a microscopic scale, these variable lenses, or?
Depends. I've seen it both ways. Okay, any other questions? All right, yeah, so you could test if you had a variable lens back here as your reference, then you could use it to test a lot of different lenses. Yeah.
So for this time and interferometer, then on that one leg right there, it's kind of like some combination of both your device under test and the mirror, like you
Yes.
have a certain shape of the mirror for the device you want to
Yes,
do.
this would be a reference surface.
Reference surface, so anything, yeah.
Yeah, so, and you need a specific reference surface for every optical element you're testing. And I've seen these things so that the Michelson interferometer was, say, most of the length of that wall over there on one leg. And then the size, the lateral size, would be like this. I've seen systems that big.
What's the purpose of it being so large?
Oh, test more astronomical lenses. Yeah, just really big aperture lenses. Yeah, and then if you're going to spend all that money to put something up in space, if it's a spaceborne telescopic system, you want to be really sure that the optics are right. Unlike the Hubble telescope. Yeah. Yeah, that was quite a blooper. Okay, so that's the Twyman Green. Now, let's go to the Mach Zehnder. you can set up a Mach Zender in a few different ways. One of which is kind of the Fizeau fringe situation. So in that case, start off with a point source, collimate it, bring it into a beam splitter. So you have a through path that goes over to a mirror. And then the other path, bring it up to a mirror. And then maybe in the upper path, we'll stick some sort of a chamber. And then here, put a beam splitter. And then over here, have an image plane. And basically, in this chamber, you could put, I don't know, you could stick, say, a wing you want to test, and then flow gas over it really fast. And then as you flow the gas over, it's going to change the density of the air locally. And so you'll get wavefronts over here that are not planar, which is what you get over here. And so you can use that lens to image the superposition of those two things and end up with Fizeau fringes over here that tell you about the gas density locally in your test chamber. So that's something that's done really all the time. So that's setting things up as a
How do you spell Mach Zender?
it's
Oh, Mach Zender.
yeah, a Mach Zender interferometer.
Wait, what is that? You said that's a gas?
Well, it's some sort of a test chamber.
Okay.
You know, could be gas, could be liquid, could be whatever. Yeah. It doesn't have to be a test chamber. It could be something that's solid, that has some slight refractive index variations or surface variations. Another possibility. These types of interferometers tend to be kind of hard to get them aligned. But once you do get them aligned, then they're really useful because you have two independent paths that the light propagates just one direction. I mean, one way through that path. You don't get the double bounce like you do on Michelson interferometer. And so they're really nice for comparing something in a path to another path. They work really well for that.
So
Yeah.
would you just do that by taking the old test chamber or whatever and putting it along the other path, bouncing it off the other mirror or something like that? Or
Well, no, so here, you'd be doing something inside the test chamber.
yeah.
And that's how you would get your variation compared to over here.
Okay. Oh, okay. Because you have to have something to compare it against.
Yes.
Yeah. Okay.
Yeah, you need a reference on.
Okay. That makes sense.
Will this give you like one measurement for the entire test chamber, or are you getting like multiple measurements throughout the test chamber?
So on the image plane, then you're forming an image of whatever's going on there compared to what's going on here.
Interesting.
Yeah. So you get an entire two-dimensional image out.
So if you wanted to compare one, I don't know, material or something, gas, whatever, against another one, could you actually do that where you place it on the other beam versus
Usually
on
you
that?
leave one beam alone and just let that be your reference beam.
Okay.
Yeah.
So is this column of light then really big, like if you're imaging a wing?
Yeah, it could be really big.
So that's just like the lens then and a really powerful point source then, or?
Yeah, powerful laser, yeah.
And you can put the image plane on either side, right? Like put it on the back or
You can, yes. Usually it's symmetric with what's going on over here with your source.
So, they both have the same optical length, right?
Mm-hmm.
So if you weren't to have something there, you just have like a full radius, like this complete.
Yes, so that's the case we want to consider next is what happens if you have a plane wave, instant, and then basically you do this. So the optical paths here should be exactly the same, right? which means that there should be no phase shift over here, so you should get all the light coming out here and pretty much no light coming out there. Okay, if you were to take, let's say, an electro-optic modulator and put it here, so you have some electrodes, hook it up to a voltage source, and then this voltage source, as a function of time, let's say you end up doing whatever modulation you want on it. And let's say that the optical path length and refractive index difference here when you apply the voltage is such that you get a pi phase shift when you apply the voltage. So here then, you end up with 0 phase shift. Here you have pi phase shift. Then when you've got a pi phase shift, what happens to the output? What's that?
Destructive interference.
Destructive interference, so you have no light coming out here. So where's the light coming out? There. And so you just made an optical modulator. So if you want to, say, modulate a beam you're going to put into a fiber for fiber optic communications, this would be one way to do it in a Mach-Zehnder. Now normally you don't construct a macroscopic Mach-Zehnder like this. Instead you do it in waveguides. So if you have a waveguide system, you could come in like this, and then do this. And so have your light source be here, and your output be here, and then this and this, those are evanescent couplers. And we talked about how you can take waveguides, bring them close together, and if you have just the right length, then you can get full coupling from one to another. Or in this case, what we want is 50-50 coupling. So half of the incident light here goes this way, half goes that way.
Just on top of your reference then.
Yeah. So then you could put an electro-optic modulator on this. If you were making these waveguides in, say, lithium niobate, then all you need is to put an electrode here and modulate the voltage between the electrodes. Since lithium niobate is an electro-optic material in and of itself, now you can change the phase of the light in this leg relative to that leg, and therefore have modulated light. And so for many, many years, that was how you would do all of the optical modulation for fiber optic communications, is with the lithium niobate Mach-Zehnder interferometer as your modulator. Yeah?
Sorry, maybe this is a dumb question, but what are the properties of an
Electro-optic material? It's basically the refractive index seen by the light propagating here is a function of the electric field applied across the material. So that is what an electro-optic material is.
So you can
So by applying a voltage, meaning an electric field, you can change the refractive
is
index.
it linear or it depends on the material?
Well, it's, yeah, there's a lot of material dependent things going on. Turns out it's also polarization dependent. But when you dig into all of that, bottom line is, yeah, you can make really fast modulators. And in fact, what you end up doing is the electrical leads that you connect to the electrodes, what you want is, because you want to modulate so fast, you have to worry about propagation time of your voltage from one end of the lead to the other. And you want that propagation time to match propagation time of the light so that you don't have phase problems when you modulate. And then that means that the leads here you have to treat in the transmission line domain, and so you have to be really careful about the electrical design of that system. And then another thing you can do is On the other side, you can put electrodes that are hooked up kind of backwards to this, and then you can have a push-pull modulation. Where here, you add positive phase, and here you add negative phase. And then you can get twice the modulation for the same voltage. And in this kind of system, the thing that always matters is what is V pi. Meaning, how much voltage do you have to apply in order to get a pi phase shift in your Mach-Zehnder interferometer? If your V pi is 3 volts, well, that's really nice. If your V pi is 120 volts, well, that's not very nice. Because are you going to modulate 120 volts at, say, a gigahertz? I mean, that's very problematic. So a lot of the design of these things gets into making V pi small. Now, in reality, this isn't how you would do it in waveguides. Instead, you come in and create a Y branch splitter and make it so it's a 50-50 splitter. And then on the other end, you bring them back together into a Y branch. And then, let's say you have a push-pull configuration, so you've got electrodes on each side. And the question is, over here, how does that work? Well, you can kind of guess that light coming in, you could split it 50-50 between these two waveguides. But bringing it over here, you know, here we've got 2 ports. Here we've got 2 ports. Here it looks like we only have 1 port. So if we adjust the phase so that we have a pi phase shift here, that means we shouldn't have any light coming out of this into this waveguide. So the question is, where does the light go? Well, it turns out that it can't reflect. There's no mechanism to reflect it. So, but it has to go somewhere. And so it turns out the other port is unconfined light. Namely, it just leaks out. It just sprays into the substrate. So, yeah. And so you probably want to have a way of attenuating that light by making the other surfaces of the chip absorptive or something. So that's really how it's done. So nowadays, when you have a high-speed fiber optic transmission system, do you find this kind of a modulator? Sometimes you do, sometimes you don't. Often nowadays you don't. Instead, what you end up with is you use something like a voltage-controlled absorber. So, and you can do that in semiconductor materials. But that's a topic for a different class. Okay, so that's Mach-Zehnder interferometers. They're extremely useful. Okay, let's do another interferometer. And this one's a fun one. It's called a Sagnac interferometer. And so for a Sagnac, start off with a point source, collimate it. Now I'm just going to show the central ray. So we can come in with a beam splitter here, and the upper path run it into a mirror, the horizontal path run it into a mirror, and then up here stick another mirror. So the horizontal path goes counterclockwise around the ring. The clockwise, or the upper path, goes clockwise around the ring. So basically what we end up with is, on this output port, light having gone clockwise around the ring and counterclockwise around the ring. So what should we get here? What's the path difference between those two directions around the ring? 0. So we should just get you know, all of this instant light should just show up here on a screen, right? Or the detector. So why the heck would this be interesting? Well, it turns out that if we take this on some axis and spin it with angular frequency omega, then we no longer have the same path length. And you can do a simple-minded analysis of this, which I'm not going to take the time to do, and calculate how much of a shift you get. But basically, if n is the number of fringes, meaning, you know, n would be 2 pi a phase shift around this thing, then delta n, one can show, is equal to 4 times the area of this thing, so this square area as I've drawn it, times this angular frequency omega, divided by the speed of light in vacuum and the wavelength.
What's that middle letter?
This one?
Yeah,
Area.
area.
So by measuring how many fringe shifts you get, or fractional fringe shifts usually, you can measure the angular velocity of this thing. Now that turns out to be extremely useful.
Just to tell you like how fast you're spinning.
Gyros.
Yep, this is a gyroscope. So, so in an airplane, this is how you tell when, you know, your yaw changes or your pitch, is you're monitoring all 3 axes of rotation with 3 of these things, all mutually orthogonal. Now, you can do that with sort of the simple-minded way. It turns out you could get rid of one mirror and, you know, do it like this with the beam splitter here, whatever. But in order to have high sensitivity to small rates of angular change, then you want a really big area. And, you know, how big can you make that? Well, once it gets to be, you know, this size, it's starting to get big. So instead what you do is take all of this and replace it with fiber and wind that fiber around many, many times, maybe put, I don't know, 2 kilometers of fiber there. And now, let's say you go around m times, so the total area is m times the area of the coil. And now you've got a fiber optic gyroscope. It's set up as a Sagnac interferometer.
What do you do? Just couple the input and output?
Yeah, so you basically, there's a splitter in here, so some of the light goes this way and some of it goes that way. And then you take another coupler out, and this would be your source. So you've got that going in, and it splits, goes in different ways, and then have a detector out here. Yeah. So that would be a fiber optic gyroscope. Another way you could play the game is have the Sagnac interferometer be a laser cavity, and actually have lasing in the counterclockwise orientation and in the clockwise orientation. And then what happens is, as this rotates, then the frequency at which the counterclockwise rotation lases becomes different than the frequency that the clockwise rotation lases at. And so now you have 2 different frequencies coming out. You can measure the frequency difference, and that's proportional to angular rotation rate. And that would be a laser gyroscope. Yeah, folks?
I'm just confused on what's rotating at that whole
The entire thing.
Okay. So the entire thing's rotating, how does that change the optical length?
Including the source, right? And so
Including the source. Everything's rotating.
Except for the image plane.
What's that?
So the image plane is what's
Yeah, the whole thing's rotating.
So how does that change the optical length and the phases of them? If they're still,
So we could do the simple-minded analysis approach, which would give us actually the correct answer, but is logically not consistent. And so to have a self-consistent theory, we actually have to go to general relativity to analyze it.
Is that like Einstein's relations, like with phonons, or?
No,
To say it has to do with tunneling.
no, but I've never actually bothered doing it. So, yeah, I mean,
Well, like
because,
my thought is like if you have like an indirect band gap semiconductor, then you can introduce phonons to like align the band
Right.
gaps. Is it like that kind of an idea, or is
I
it?
don't think so.
Okay, sounds really
It's a
interesting.
Doppler thing.
Yeah, I mean, you can get this from a Doppler sort of approach. You just calculate the time difference between the two different rotation states. But even though it gives you the right result, it's not a self-consistent theory.
Interesting.
So is this rotation like really fast?
Well, so if you're on the next time you do a transoceanic flight, the plane that you're on has 3 laser gyroscopes inside of it. And it will measure very small rotational changes and do it really accurately. For any of these gyroscope approaches, the name of the game always comes down to angular drift. You know, how many degrees per second or per minute or per hour is the drift in your measurement, meaning it looks like there's a rotation, but there really isn't. And then that gets back to a bunch of noise properties. So, and what you want is to have a really, really low angular drift. I used to know the numbers off the top of my head, but I don't remember them anymore. But for an airliner and the really expensive laser gyroscope that goes inside of it, it's fractions of a degree per hour. I mean, it's really small. So, yeah.
And so, just, you put this at the spot where the airplane rotates, at the point of rotation usually for the airplane, is that how?
Anywhere,
Okay.
yeah, it'll pick it up anyway. Yeah, I mean, on the one hand, you could argue, maybe you need to be at the center of gravity, but yeah, it doesn't really matter anyway. Yep.
So this isn't actually, it's stationary within a text rotation, or is it
It detects when it rotates.
when it rotates? So it does stay stationary, so it's not like it's inside of something where we're actually spinning it out to begin with.
Correct. So you basically take this, bolt it onto your airframe, and then when your airframe rotates, this will tell you. Yeah.
What was delta N?
That's the fractional fringe shift. So basically, 2 pi phase difference here corresponds to 1 fringe shift.
Okay.
So where does the laser get all of this area from? Like there's area square, there's the area created by all the circles of the fiber, and then what's the area that's making the laser circuit?
Oh, so if this now is optical gain material, and so this is the path that you're lasing over,
Okay.
then that's the laser gyroscope.
So why is that better than just the non-optical gain material version? The area is the same then, right?
Yeah. Oh, yeah. Yeah. You don't have a win in terms of area, but it turns out that in measuring a frequency difference, you can be really, really precise. It's easier than measuring a fringe shift
So
because
it's really a benefit in the measurement.
yes, because here on a fringe shift, what if we measure say n here, which is the same thing as measuring delta phi? What does it look like? Well, it looks like this. And where's our bias point? Well, we're sitting right there, with no rotation. And so, how small of a difference in intensity can you measure without getting swallowed up in noise? That's a bad place to sit. You really want to sit over there. And now, if you have a little bit of change, you get a much bigger change in the radius. And in fact, with a Mach-Zehnder modulator, it's the same deal. You really want to be sitting there and not there. And so what you do very deliberately is you take one of these path lengths and make it longer than the other one. So you're biasing at pi halves. Because at 0 or at pi, you basically have no sensitivity for small changes in phase. So, yeah. Okay. All right, so now what we want to do for the last part of today is go back to polarization and see how that kind of fits into this whole interference thing that we've been doing. So far, when we say polarization and interference, what do we know?
Do they have to have the same polarization to interfere?
Yeah, same polarizations can perfectly interfere.
Arbitrary.
Orthogonal polarizations don't interfere. And if we have something that's not perfectly orthogonal,
Then it interferes kind of in components, I guess.
yeah, it's only the component of one that's in the direction of the other that will interfere. Okay, so let's say that we have a system where we've got light propagating in the z direction, and it's just some general elliptical polarization. In which case, we can write the Jones vector as ax, ay, e to the j delta, with delta being the phase shift of the y relative to the x component. And let's say that we stick a polarizer here at, in the x hat direction, then what's going to come out? What am I going to get?
You get the component of the elliptical polarization in the x direction.
Yep, so that'll be AX. On the other hand, let's say I stick a polarizer here instead in the y hat direction. And so what will I get out? Just the y component. Okay, so we've been through that. That's pretty trivial for us now. Now, we can think of the x polarized piece and the y polarized piece as being two different beams, if we wanted to. And because they are orthogonally polarized, they do not interfere. But we could play a game and make them interfere. And let's see how that works out. Let's say that we take a polarizer and stick it here at 45 degrees. So if I draw the x and y axes, I have this polarizer at 45 degrees, and I have the x component here, which is ax, and the y component here, which is ay e to the j delta. And the question is, what comes out of my polarizer?
It's going to be light at 45 that has kind of each component.
Mm-hmm. Yeah. And so if we draw or we write the Jones vector in the x prime, y prime frame, where this is x prime and this is y prime, then I'm only going to have an x prime component, right? So the question is, well, how big is that x prime component? And it's pretty easy to figure out. We could do it mathematically, or we could just do it with some intuition. And let's do the intuition approach. The amount of AX that gets passed by the polarizer is just the amount that's in the direction of the polarizer, right? Mm-hmm. And so that's going to be 1 over root 2 of AX. And likewise, for AY, it's just the component in the direction of that polarizer, which is 1 over root 2 AY e to the j delta. Okay, so then question is, what's the irradiance of the light that has come through the polarizer? Well, it's going to be magnitude squared of the electric field divided by 2 times the impedance of whatever medium we're propagating in. And so if I call IX, AX, actually AX is real, so I can just square it. And IY, AY squared over 2 times eta. In other words, the irradiance of the X polarization of the instant light and the irradiance of the Y polarization of the instant light. And I work out what the irradiance is after we pass through the polarizer. The 1 over root 2 is common. I can pull it out. That's going to give me a 1/2. And then I'll have an AX squared over 2 times eta. That's just IX. I'll have an AY squared over 2 times eta. That's just IY. And then I'll have the cross terms. And that will give me 2 times square root IX IY cosine of delta. Oh my gosh. Doesn't that look familiar? That's just the interference of 2 collinearly propagating beams. And notice what the phase difference is. Delta. The phase difference between the Y and the X components. So by using a polarizer and inserting it here 45 degrees, I can force interference between the X and Y components of my polarization state.
Which kind of makes sense because how we just rotate it, right? Like we kind of think of it like a rotation.
Well, it's not. We're picking off a piece of the X and a piece of the Y
That happen to be in the same direction.
that are in the same direction. That's what the polarizer does. So in other words, we can use a polarizer to force orthogonal polarization states to interfere. Because this light that I wrote coming in, I just said, general elliptical polarization. I didn't say how it got it. But maybe I got it from the X polarization state coming from some beam path, and the Y polarization state coming from some other beam path. And I want them to interfere, but they're orthogonal states, therefore they won't interfere. But aha, I have a solution. Just stick in a polarizer at 45 degrees, and voila, they interfere. And the phase shift between the X and the Y components is the phase difference.
And you just lose half of your power, is that it?
Lose half your power.
Okay.
That's right. So for the price of half your power, you can force interference. That's a handy trick. So let's see how we can use that handy trick.
How did we get the last term, this last equation?
Right here?
The,
Well, so we're doing magnitude squared, so it's this thing times its complex conjugate. You know, and so this is that term squared, this is that term squared, this is this times the complex conjugate plus this times that complex conjugate. Yeah. Okay, so let's see if we can figure out in the last minutes of class how you can use this. And as an application, let's turn to the field of microscopy. So in microscopy, you have some sample. Let's say it's here, and you stick it in a microscope, and so with the microscope, you have light coming in, it goes off a beam splitter. Let's say you're imaging and reflection. So the light comes in here, and then it reflects. And actually, I'm just going to use the same path for reflection, and we go through here, and then we basically image. Normally this is your eyeball, or it's a camera, whatever. But ultimately, we form an image of this surface to that surface. So there are different ways in which we can operate a microscope. The way that you're all familiar with is called bright field. And so for the bright field operational mode, this is the setup. And basically what's happening here is any variation in reflectance on that surface shows up as a variation in intensity at the image. In other words, if this piece right here reflects a lot, it shows up, I get light over here. And then if this piece reflects a lot, it'll show up over here. But in between, if it doesn't reflect very much, then I'm just not going to get much light there. So in other words, contrast in the image maps to reflectance in the object. Okay, so that is bright field imaging. Now, what if I had a surface that was coated with, say, gold or aluminum, whatever? So it reflects the same everywhere. There's no change in reflectance. But let's say that I had some roughness here, and then it was flat. Then the question is, if I take that, stick it into my microscope, what will I observe? And there's no difference in reflectance anywhere. It's all coated with a thin film of aluminum. And there, to think about how this works, you need to think about that first lens. In fact, let's make it a little smaller to make it more obvious. That light that comes in here makes it into our lens. Light that comes in here reflects back and makes it into our lens. Light that comes in here
It's
is scattered. So some of it's going to go over here, some of it's going to go here. But notice only the light that is scattered into this cone makes it into the lens. And therefore only that light will make it into our object. And because we're losing light that's scattered outside the entrance aperture of the system, this rough place is going to appear darker than the other places. So Mala showed me an image a week or two ago in our microscope of something, and says, why does the channel look dark? And it was for exactly this reason. The surface of this channel had some scattering properties, and so it was just scattering light outside the entrance aperture of the microscope. Okay, so it doesn't have to be only reflectance to map into contrast in the image. It could be scattering. And in fact, we can make use of that to create an entirely different imaging mode called dark field. And in dark field, what we do is we have our lens, and we deliberately block the central portion of it, and we just have an annulus through which we can accept light. So if we look from here, what it looks like is a dark center where no light goes through, and then a ring that's transparent, and then it's dark out here. So in other words, we're only going to accept light that comes through that thin annular ring. So what happens then is, with our surface, let's say we have something that looks like this, basically light that comes in here, it's going to go back and just get blocked by the aperture. And light that comes in here, it'll get blocked by the aperture. Light that comes in here, it's going to get blocked by the aperture. The only light that makes it through the aperture is light that goes through this little annulus. And the only place that will send light through the annulus is a corner where it scatters light. Yeah. Basically, now we have an edge detector. So in our image, we're imaging edges, because that's the only thing that will send light through this little annular ring. So that's called dark field imaging. If you have little tiny specks of dirt on your sample, then dark field is a great way to see them, because those are the only things that are going to light up when you look at it in dark field. If otherwise it's more or less flat. Or if you just have, let's say this is silicon, and you've just got an etch here and you're doing, say, 200 nanometer deep etch. You stick that in the microscope, well, everything's going to look kind of the same because the reflectance is the same everywhere, except on the edge, maybe you'll scatter a little bit of light outside the entrance aperture. But if you flip your microscope into dark field mode, so you're doing this, suddenly those edges just are bright. You'll see them very clearly. Okay, so,
Excuse me.
Yeah.
When we set up the problem, you said that polarizer X is rotated 45 degrees, or
Mhm.
yes?
yeah, we set a polarizer at 45 degrees to X.
Okay.
Mhm.
And we do it on purpose because of some applications.
Yes, we do it on purpose because we want to force interference between the two orthogonal beams.
Okay.
So in your case, if you set up the antenna 45 degrees with respect to the ground plane, then you're going to force interference between the TE and the TM polarization in your system.
I will come to you soon.
Okay, all right. Okay, so now in our last few minutes, let's talk about a different imaging mode, and this is called Nomarski, or it's also called differential imaging contrast, or DIC. If you go to the microscope in my lab, there's this little thing you can rotate, and you'll see, BF for bright field, a DF for dark field, and you'll see DIC in another one of the points where you can operate. Okay, so what is that? Well, let's say that over here in our bright field image, let's say that we are looking at our sample and our field of view is circular. What if we could take a copy of that field of view and shift it a little bit and force light between the two to interfere? Then what would happen? Basically, in this direction, let's call it X, we would see the derivative with respect to X of the height of the sample. Because, let's say my sample, let's say I do a cross section through here, and my sample looks like this. And let's say I coat it with aluminum, so no change in reflectance anywhere. Then my copy here is basically shifted a little bit like this. And then if I force them to interfere, then what happens is zero phase shift right here. So this will appear bright. Zero phase shift right here. So let me just kind of draw it down here. This region is bright right here. This region is bright over here. This region is bright. Here I've got some phase difference. So I'm going to get some destructive interference. So it's going to look darker there and darker there. And this is called shearing interferometry. So we're taking an image, making a copy, shearing it a little bit, forcing it to interfere, and then when something is going on where we have a height variation, it's going to show up as a fringe. When there's no height variation, it's just going to show up as a bright spot. So it's another way of accentuating edges. So the question is, how do you make this happen? And that's where this comes into play. So what we do is we start off with polarization that's 45 degrees here to the board. So we've got a component out of the board, component in the board, reflects, And over here, what we do is we stick in something called a Wollaston prism. And what that does is the light that is, say, in the plane gets redirected one way, and light that is out of the plane gets redirected another way. And then these two beams are slightly shifted. When they come back up and reflect through, the Wollaston prism then combines them, so they're sitting on top of each other now. And our information is encoded in the two orthogonal polarization states. So up here, we stick in a polarizer at 45 degrees to those two states, and then we force interference, and now we get this shearing interferometry effect. And so that's called differential interference contrast, or Mimarski microscopy. And when you buy a microscope, this is a really useful thing to have. And of course, it'll cost you an arm and a leg. Okay, well that's it for today. We're out of time. So enjoy the homework. Turn it in next time. And we'll see you Thursday.
The Wollaston prism, you said its purpose is to just divide the polarization states?
It takes the two orthogonal states and basically causes them to angularly deviate from each other.
Okay.
So they propagate a little